Morning, everyone. So we're going to continue with our introduction section here. Yesterday we had a look at safety. Hopefully you've had a chance to look over the package and read over some of the details there. For the rest of our notes here, I don't mind how you keep your notes, so I would just encourage you have out a piece of paper for yourself. You can just copy down the notes as we go through it here, especially when it comes time to actually practice through questions. It might be good just to pause the video, try the question out for yourself, and then you can resume the video and see how you did that way. So we'll do this section here on conversions. So to start off here, I just want to rehash with you here in science. We measure units with an international system. Those international system units here are called SI units. The reason why it's SI here, this is only the French I'm going to mention to you, I promise. So this is System International. Madame would be worried that I'm teaching you French. So System International, basically it's an international system of units. So we're going to start off here. This shouldn't be new to you, but at least I want to make sure that we're all on the same page as we start off. We're going to start off with a quick table here. Depending on what quantity I want to be measuring, I'm going to mix and match it with the corresponding SI unit. So in science, what unit do I want to put it in before I crunch through my formulas, things like that. Surprisingly, this list here is actually fairly short. So for starters here, we're going to start off with measuring length or measuring distance. You can use uppercase L or lowercase l, it doesn't really matter. For length, if you think about all the units that are potential, you can say inches, you can say feet, you can say kilometers, things like that. We choose, hopefully you can remember, meter, m, to be our SI unit. So there are things that are longer than it, there are things that are shorter, centimeters, micrometers, things like that. So length, we just prefer to convert everything over to meters instead of inches and feet. When we measure masses in science, we can use m as a subscript, so like m equals something. So because both of these are m, you have to read it from the context. So for example, if I had a distance and it was, let's say 10 m, because this comes after the number, I would read this as 10 meters. If in contrast I said m equals 10 here, the mass is equal to in this m here, I would actually treat it as mass instead. For the SI unit here, it is actually best to say the SI unit for mass is actually the kilogram. So kilogram is going to be kg. It's just that although in particular areas of chemistry, kilogram does make sense, kilogram is actually a ton of chemical. We're going to see in our labs, we're only going to use a handful of chemicals, only grams worth for a lot of our conversions. So I'm just going to make an emphasis here, at least in chemistry. In chemistry, we instead use grams, so we just use a G. And I particularly like that because in a second we're actually going to rehash some of these prefixes here. We're going to find that kilo, this K here, is actually not special to just gram. You can have a kilometer, a kilosecond, you can have kilo anything, and a kilo represents the same thing for whatever quantity that you're talking about. I just mentioned seconds here, so if I'm measuring a time quantity, so t, we have things that are longer than seconds, so things that are like minutes, years, months, things that are shorter, like a millisecond, nanosecond, things like that, but seconds seems to be convenient for us here, and just the S for seconds there. This is why in physics, when you do this SI units here, they call these MKS units. The M for the meters, the K for the kilometers, and then we have the S for the seconds. So meters, kilograms, and seconds, so MKS units. We're going to do two more on this table here. We're going to plot temperature. So temperature, I'm going to use capital T just to make it different from the time one that we had earlier. And for temperature here, because temperature here is going to be related to the average energy, and energy has to be a scalar and energy has to be positive, we prefer to have a temperature scale. Fortunately, it's very similar to Celsius, but we're going to switch over to the absolute scale here. This is called Kelvin. When we do temperatures in Kelvin here, we don't say 0 degrees Kelvin, we just say 0 Kelvin. Right? 0 Kelvin is a guy called absolute zero. It's a theoretical value. Basically, the particles would be traveling so slowly that they would actually be stopped. We've gotten pretty close to 0 Kelvin. We've probably gotten to like a millikelvin or microkelvin here, like 0.0001 Kelvin. But hypothetically, we can't get to absolute zero. The one that might be a new one here is, especially in chemistry, when we start talking about an amount of chemical, surprisingly, we're going to use N for that. So I already used M for mass earlier. In this case here, we're actually introduced our first key term from our stoichiometry chapter. This one here is the unit moles. So mole, or we can just say mol. And just think of a mole here at the time being, it's like a box. Inside the box is containing many, many particles, and it basically is pre-packed. If I have 5 boxes, I know exactly how many are inside because I know how many are inside one box. There are actually 2 others. I think one of them is current and one of them is luminosity, but they're not super important for us in chemistry, so I'll leave the list off there. Again, the emphasis here is, how come this list is so short? Aren't there other things I can measure in science? Can I measure things like area, density, things like that? Speed? Where about all those other ones? All the other ones here, let me write this down in words for you here. All other quantities can be derived from these units. So let's think area for a second. So let's say I have a square, area is length times width. Well, length and width are both measures of distance, so I just go distance times distance. There, I got an area. Or if I said speed, I need to know a distance divided by speed. So if I take a length divided by time, that would give me speed. See if you can do for yourself here. What about density? Density is supposed to be mass divided by volume. We do have the unit for mass, no problem. That should be kilograms. Again, in chemistry, we'll use grams. Volume is sort of 3 dimensions of distance, so per centimeter cube or per liter there. So in that case there, it's divided by length cubed. So you see how we can actually derive all the other physical quantities based on this set of units here. So it's nice keeping this list fairly short. The thing we do have to introduce, however, is depending on what we're actually measuring, these are nice as base units. These are nice as nice references because it's easy to think about things that are bigger and smaller. But what we want is, especially when we start measuring things that are really far, let's say the distance from here to the sun, I don't want to take a meter stick and count how many meter sticks from here to the sun. It's going to be like 1 billion meter sticks. Instead, what I'm going to do is I'm going to factor in what's called a metric prefix. Again, I know this part here isn't new. But what I'm going to do is a metric prefix. Actually, our counting system is with metric. It's nice because everything is in powers of 10. We're going to add what are called prefixes. These are little syllables that come before words like kilo that roughly tell me the power of 10. It roughly puts me in a certain decimal place so that I'm not having to carry around huge number of zeros or 0.00, many zeros like that. So just like earlier here, I want to set up a table. This time our table, I'm going to introduce for you the prefix. So what is that syllable that we put before the word? I'm going to emphasize what's the factor that prefix says, and then for a couple of these I'm going to give you an example. All right, so that's our heading for the next table. We're going to start prefixes. Again, you have seen many of these prefixes before. We're going to start from biggest to smallest. So let's start off here from giga. Same prefix as we have for gigabyte. So gigabyte is going to be a capital G as a prefix. That factor there actually represents 10 to the 9. Now, when we're in positive powers of 10, it's fairly easy. So, for example, if I have 1, I mentioned this is a prefix that can be mixed and matched with any base unit. This time, let's mix it with the meter as the base unit for length. So, what is 1 gigameter? Well, that's 10 to the 9, or that's 1 with 9 zeros. That's going to be a billion meters. Is that 9 zeros? 3, 6? No, missing a zero there. So that's going to be a billion meters. So back to my analogy of measuring the distance from here to the sun, instead of saying, oh, it's like 100 billion meters, if I'm already in a power of a billion, I can just say, oh, it's 100 gigameters, right? So because the gigameter is hiding some of that power of 10, I can keep my numbers fairly small. For positive powers of 10 here, the power itself tells you exactly how many zeros come afterwards. As you step down from giga here, there actually are 2 prefixes for 10 to the 8, 10 to the 7. It's just we don't use them very often, so I'm just going to skip them. Let's skip down to mega. In a similar way here, we have a megabyte. Right? Computers do like binary systems, so they're not exactly spot on a billion, or in this case here, spot on a million, but at least it is that rough order of magnitude. So we're in the millions here. Again, I could have mixed and matched this mega with anything from earlier. Let's mix and match it with mass. So let's say 1 megagram instead. Well, 1 megagram here would be equivalent to 1,000,000 grams. Right? That actually, 1 megagram is actually called 1 ton. So 1,000 grams is a kilogram, and then 1,000 kilograms is actually 1 megagram, which is called a ton. So there's the mega prefix. Again, there's 2 other prefixes here, 10 to the 5, 10 to the 4. Because we're metric, we're going up and down in powers of 10 here. we're going to go down to the most common ones here. You will need to memorize these prefixes here, especially these middle ones that I do with you here. Pretty much with more practice, you're going to be more comfortable with this. For kilo as a prefix here, kilo stands for 1,000. So earlier when I had a kilogram, it means I have 1,000 grams. But like I mentioned, kilo isn't special for grams. I can do 1 kilo. I can mix and match with anything. Let's mix and match it with seconds instead. I can have 1 kilosecond. This time I'm measuring time. These my base unit is seconds, but this would then imply here 1,000 seconds. So there's kilo. As we go down from there here, we're going to go to hecto. So we're not going to skip any this time. So back in the olden days when people owned hectares of land, it had something to do with 10 to the 2, so 100. If we keep going down from there here, we're getting pretty close to just having our base unit. Our base unit is just our plain old meter or plain old gram here. That's the case here where we have no prefix, and no prefix means the order magnitude is just 10. It's just 1, so 10 to the 0. What we're going to find is the prefix that's above and below this base unit here. They both start off with D. In fact, I'm going to spell both of them here. One of them is deca, one of them is deci. Make sure you know it's the deca one that actually goes on top. Deca is sometimes spelled D-E-K-A, but I spelled it D-E-C-A just to make a quick observation here. Deca, now they both start off with D. They can't both be D as a shorthand here. We're going to actually put D-A for deca and just D for deci. So just matching up your powers here again. So deca would be 10 to the 1. 1 is just 10 to the 0. And then in this case here, as we drop into the negatives, we actually go 10 to the negative 1. Negative exponents means we're actually in the denominator. So it's 1/10. And careful for decimals here. Let's say I go back here and I have 1 decimeter. In that case there, I have 0.1 meters. So we're still measuring length here, but you see that this, we needed a first power of 10 here just to get past the first decimal place here. It doesn't exactly match the number of zeros afterwards. So just watch out when we get to the negatives there. Let's keep going downwards from there here. If I cut up a meter stick into 100, I get a centimeter. So centi is the prefix for 100th. So this is 10 to the negative 2. It can mean 1 over 100. What this table is trying to show you here is if I have one, let's do centigram, right? It could be any base unit here. 1 centigram here would be equivalent to 0.01 grams, right? So centi puts you in that rough power of 10. Or these are all just true relationships here. You can reword them. If I really don't want to see this decimal here, I could equally well have said here, well, that would mean then 100 centigrams is also 1 gram. So if I have 100 hundredths of a gram, so 100 of tiny little thing, I can make one big thing. There are many ways you can represent this, but at least on this table here, it's just saying, imagine I have 1 of the prefix, and here's the corresponding power of 10 that comes with it. Let's finish off with a couple of smaller prefixes here. Let's switch down into milli. So if I cut up a centimeter into 10, I'm going to end up with a millimeter. Milli is going to be lowercase m. Now this is a prefix, so this m is still going to become before your base unit. So it could be a let's do a millisecond. That's going to be 10 to the minus 3. It's 1,000th in the opposite way. So this one here, again, as decimals, you can say, let's say 1 millisecond is 0.001 second. It's 1,000th of a second. It's shorter than a second. So that one there is milli. Let's do a nice mirror here. On the other side, let's skip 10 to the negative 4, 10 to the negative 5. Going down to a millionth, instead of being a million bigger and getting mega, let's go a million smaller. We're actually going to get a micro here. Micro, unfortunately, we've used the capital for mega. We've used the lowercase for milli. In this case here, we're going to switch over to the Greek. The Greek equivalent to m is actually this mu unit. So in this case here, make a note to yourself, this is the Greek letter mu. It's like a U with a slight tail on it. And in that case there, that does mean 10 to the negative 6. If you ever hear the word here, 1 micron, 1 micron is actually equivalent to 1 micrometer. And in that case there, this is equal to, with 5 zeros and a 1 meter. So it's a millionth of a meter. I would need a million of these tiny little guys here to end up getting 1 full meter. So it's taking a meter stick, chopping it up in 1,000, and we get small tick marks of a million, and then chop of 1,000, and then you chop it up into 1,000 more than that. So we have a millionth of a meter. That's 1 micron. Again, just a nice parallel image here. Let's skip 2. Let's skip 10 to the negative 7, 10 to the negative 8, and let's go down to 10 to the negative 9. When we start talking about wavelengths of light, we'd like taking in this scale here, and these ones here are called nano. and this one here is going to be just n for short. So for example, when we get to chapter 2 and we look at some electromagnetic wave and we say red light, so red light has a wavelength of 700 nanometers. That's this prefix nano. So in that case there, it actually implies there 700 nano meant 10 to the negative 9, so 700 times 10 to the 9 meters. Your calculators, when you punch this in, it'll automatically convert that to 7 times 10 to the negative 7. Is that okay? I thought nano was 10 to the negative 9. Well, you see here, yes, nano by itself does mean times 10 to the negative 9. It's just that for this red light wavelength, we actually have hundreds of a 10 to the negative 9. So if I pick up 2 more powers of 10, we end up back in times 10 to the negative 7. For the time being, we're not going to worry about rounding. We'll worry about it as a separate lesson in tomorrow's case. In this case here, as numbers are starting to get really big and really small, you do need to memorize these prefixes here. I do want you to just review just scientific notation. So scientific notation, it's convenient, used to express. It's just a way of writing it. Used to express very big or very small numbers. And there really is no one saying, oh, when is it big enough that I have to use scientific? I pretty much say, if it's useful, use scientific notation. There will be one case in the rounding that we do in tomorrow's lesson here that we have to put in scientific, but we'll get to that. Scientific notation as roughly this format. So let me give you a sample number here. 1.2 times 10 to the 3. Now that number by itself is not all that big. That number is 1.2. This one here is called the base number. For your base number, the rules are your first digit has to be between 1 and 9. So this cannot be 12 times 10 to the 3. It can't be 0.12 times 10 to the something. Okay, that first digit has to be between 1 and 9. And what we've separated off is this times 10 to the power of. This 10 to the power of just puts my decimal place in the right spot. It makes me add the correct number of zeros. In this case here, we're going to call this the order of magnitude. In tomorrow's lesson, when we talk about significant figures, there actually is no significance to this part here. It is just there as a placeholder to tell me, oh, I've actually picked up 3 powers of 10. It's like this number 1.2, but I've moved the decimal place 3 over. So we're actually talking the number 1200. So that there is scientific notation. We separate our base number from order of magnitude. Again, that number was not overly big. I may not need to do that. Sometimes on worksheet they say put everything in scientific. That's just for practice. Like I mentioned, if it's useful, use it. If not, just leave it in what's called standard form. Standard form is the way we typically write the number. You could also call scientific notation sometimes exponential form while I'm at it. So if you see that exponential form, it means write the order of magnitude as an exponent. It can also be used to write really small numbers. So it could be, let's say, 4.56 times 10 to the negative 7. We know the 10 to the negative 7 is a tiny number. So in fact, what's going to happen is it means take the 4.56, good, the first digit is between 1 and 9, but take that decimal and move it 7 times to the left. So imagine going 1, 2, 3, 4, 5, 6, 7, 8, 9. I definitely don't want to draw that number all the time. Anything that I pass by has been a 0, so we're actually talking about that number there. So it's used to express a very tiny number here. If you have units, the units come right after. Maybe that's centimeters or whatever you're measuring. Your calculators have pre-programmed this scientific notation. Let's say I wanted to type this number in. I can actually type it in. You punch in the numbers 4.56. I can press in sure. Brute force it. I can go times 10 to the hat negative 7. That's perfectly fine. Times 10 to the power of. What your calculator's done is they've actually done a shortcut for this middle part. We do scientific notation so common in science that they've actually put in a new button. You can take out your calculators, make sure you can see this button for yourself. It's either written as EXP, an EE, or even better yet, they even show you what they're doing, times 10 to the power of. So by doing that, we can actually retype in this number here. I can equally well just type this in 4.56. I press that EE button and just type the power that comes afterwards. One advantage that's not immediately obvious right now here is by putting that EE, it knows to put these two numbers together. It has artificially put brackets around it. So we won't need to worry about these brackets later on. That's just convenient for you. Just be careful, however, although the exponent, this EE here, does mean to the power of, what's the difference? Just think here. What's the difference between if I go 2 hat 3 versus 2 EE 3? Right. Well, 2 hat 3 means to the power of 3. This time it's 2 taken to the power of 3, so 3 2's multiplied together, that gives you 8. In this case here, it also means power 3, but that EE represents it's the 10 that's taken to the power. So this means 2 times, when 10 is to the power of 3, it actually is a totally different number. So in this case here, both of them are to the power of 3, but we actually are referring to different numbers. So that's going to be just exponential notation there. Now what I want to do here is, because we have so many prefixes, we have so many units, we want to be able to interconvert from one unit to the other. So let's finish off our lesson here, and let's take a look at our strategy to do unit conversions. This strategy here, I believe you're first introduced in grade 10, but every year people forget it, so I'm just going to keep rehashing it. Very powerful way we're actually going to set this up. Basically, we're going to follow the structure. So for a conversion here, there's always going to be some unit that I'm asking for. So I'm just going to put question mark. Here's the unit that I want. We're going to start off with the unit that we have. So the number, I have 5 centimeters. So I just start off with that one there. And how we're going to accomplish the conversion is actually setting up a conversion factor by going multiply by a fraction. Just like numbers would cancel out, this is in the numerator, I would put the unit on the bottom to cancel it out. The halves cancel, and we end up putting the unit that we want up above. So sometimes they refer to this as factor label method. They basically put on the labels of the different units, and you basically want to cancel all the units that you don't want and just leave behind the one that you do want. So let's start off fairly simple here. Still write out the question for you here. How many grams in 3.5 kilograms? Okay. If you wanted to convert a mass of 3.5 kilograms back into just the base unit grams, how many would I have? Hopefully you know the answer right away, right? A kilo is 1,000. I have 3 and a bit, so it's going to be 3,500. Just humor me for a second here. I'm going to show it to you with this conversion. Here's how this works here. I'm going to go question mark grams, because I know my final answer is supposed to be grams. Always start off with the number that's given to you. This one here currently is 3.5 kilograms, like that. We haven't done any conversion yet. To do the conversion, I purposely write out my own fraction, so multiply by a fraction. If this is the first time you're seeing this part will feel a little bit weird, we're just going to focus on the unit part first. So right now my unit 3.5 has kilograms. I don't want kilograms anymore. Kilograms on top has to cancel kilograms on the bottom. That way it cancels. The unit that I want to be left with here is actually going to be the gram. So I want grams on top. You'll notice I've just dealt with the units. I haven't actually done any numerical values, numerical conversions yet. That's your first step. Now what we need is one true relationship between these two units. After all, we need to convert kilos to grams. I'm going to find the easiest way to do it. If you look at your fraction, you decide which one is bigger. The one that's bigger, put a 1 beside it. So between kilograms and grams, you can check the table up above. I know a kilogram is larger. When you put a 1 beside the bigger one, the other one is going to be, in this case here, 1,000 grams. So it's going to be a positive power of 10. 1,000 grams makes a kilogram. This is sometimes referred to as a unitary rate. So that's our conversion factor, or conversion factor. So conversion factor. And the reason why it says unitary is because at least one of the numbers is actually a 1. Right? Now, although I show my work like that here, in terms of typing into the calculator, it's very simple. I go 3.5, because the 1,000 is on top, 3.5 times 1,000 gives me 3,500, what I expected from earlier. Let's imagine trying to just check my work here and go backwards. Let's imagine starting from 3,500 grams, let's reconvert it over to kilograms. So if I ask the question backwards, if I said, how many kilograms would you have with the 3,500 grams that we just did? It shouldn't surprise you if one way was times 1,000, the other way should be divide 1,000. Again, just humor me for a second. We're going to set up this unit cancellation method here. I have 3,500 grams. I'm going to set up a separate fraction. I'm going to go through just looking for the grams itself. So grams is currently on top. I'm going to put it on the bottom to cancel out. What I want kilograms on top there. Let's decide which one is bigger. Oh, kilo is bigger. Let's put a 1 there to make it a unitary rate. You check your metric prefixes up above. A kilo is 1,000. So 1 kilogram is actually 1,000 grams. Again, that's where your work shows you here. Because now that 1,000 is in the denominator, I would actually type this in. Don't bother type times 1. Doesn't change your number. I go 3,500 divide 1,000, and you get back 3.5 kilograms. Right? Where one way was multiplied, the other way is going to be divided. Now, the advantage of doing this one here is I can throw a few little twists to the question. So new question here. Let's try to figure out here how many centimeters if I have a wavelength, let's say 550 nanometers. Okay. Now, in comparing this question so far, sure, the base unit here is now no longer a measure of just mass and grams. It's now meters, so the base unit is distance. The bigger difference is previously it was changing from something that had a prefix to something that has no prefix. Now what I want is I want you to convert nano, which has a prefix, and centi, which also has a prefix. So let's just try out our strategy here. You can try it out for yourself as well. I'm going to start off question mark centimeters because I know my final unit is supposed to be centimeters. This is supposed to equal, in this case here, 550 nanometers. I'm going to set up my trusty fraction to convert the units. I'm going to focus on just the unit part, so nanometers. Put nanometer down below. I want centimeters up here. Here we encounter a problem, however. Although the units themselves would have canceled out, I may or may not know the conversion between one prefix to the other prefix. So this is a strategy that I would normally use. I know nano is a billionth. I know centi is 100th. But that's a billionth of the base unit, that's 100th of the base unit. What I'm going to do is, I know eventually prefix to prefix, but let's just go the nano prefix, let's just go back to the base unit first, because I know at least that's a billionth. The advantage of doing this setup here is you can tack on as many conversion factors as you have. Well, now I have meters on top here, put meters on the bottom to cancel out, and then go to centimeters. So you see how you can tack on as many fractions as you want. Top unit also always cancels the bottom unit, and we basically go through. Let's decide which one's bigger. Let's do the first one here. So between centimeters and meters, which one's bigger? Hopefully meters is bigger here. We're going to put a 1 beside the bigger 1. Okay. Put 1 beside the bigger unit. So 1 meter. Back when we check our table, centi, the centi prefix does mean 10 to the negative 2. But the reason why putting a 1 beside the bigger unit helps is now that I have 1 of a huge meter, I can't have 10 to the negative 2 centimeters, right? I can't have 0.01 of a tiny unit. In fact, what's going to happen here is even if the prefix by itself would have had a negative power, this prefix here is now positive power. So what I'm saying there is, although from earlier we said 1 centimeter is equal to 10 to the negative 2 meters, you can equally well say, well, what if I have 1 of the bigger unit? 1 huge meter is actually 10 to the positive 2 centimeters. 100 centimeters make a meter. So once you put a 1 beside the bigger unit, even if the prefix by itself had a negative power, it's now going to switch to become positive. If it was positive again with it stays positive, no problem. So let's do the same here. I know nano is smaller than a meter, so let's put a 1 beside the bigger unit. Based on my unit cancellation here, that 1 had to be on top. Nano by itself was the prefix 10 to the negative 9. It doesn't make sense. 10 to the negative 9 of a tiny unit is one big unit. In fact, what I want to change is the negative power into a positive power. And I want to say, if I have a billion, tiny little billionths of a meter, that adds up to 1 of the big unit. So in this case here, so far the conversions have been nice because they've been metric, they've been powers of 10. So 550 is going to pick up 2 zeros, it's going to lose 9. So overall, we're going to lose 7. So if you imagine the number 550, the decimal would have been here. If I lose 7, I'm going to go 1, 2, 3, 4, 5, 6, 7. Decimal's over here. Right? That's a number here. That's probably better if I wrote in scientific notation. You could just count your way back. So the number is 5.5 times 10 to the negative 5. You could equally well have done that here. If I know we're going to pick up a factor of 7, you could have said, well, let's take 550. Let's pick up a factor of 10 to the negative 7 like that. And then if I convert it back into just scientific notation, where the first digit is between 1 and 9, I move it over by 2, and I end up with 5.5 times 10 to the negative 5. Again, we'll come back to this in tomorrow's lesson when we talk about rounding. For the time being, I just want the numerical value correct. Sometimes your calculator, when you type this in here, sometimes it will also format it 5.5 e negative 5 like that. That's just shorthand for your calculator. I still want you to rewrite it as the full times 10 to the power of, because that's what that exp, that's what the power of 10 actually shows you. Careful, sometimes the exp is squished really tightly into the corner. It still is important because that tells you where the power of 10 is going to be. Let's do 2 last examples, and then you can work through your worksheet for some more practice. Let's see how this conversion works out here. Let's go from 55 kilometers per hour. Unfortunately, neither of those are the correct base units. distance is supposed to be in meters, and time is supposed to be in seconds. So while my sort of car odometer here reads kilometers per hour, it's convenient. This is slightly faster than the speed limit here. I need to convert it back into the SI units before I can actually do any science and do any math with it. So let's try it out. We know our final unit is supposed to be question mark meter per second. We now have a problem because this 55, the fraction is already in the unit. In this case here, if you have a fractional unit, what I want you to do to start off is to write out the fraction explicitly. So when you say 55 kilometers per hour, what you mean is 55 goes to the top. You manage to travel 55 kilometers. When you say very quickly per hour, what you're meaning is all over 1 hour. For every hour that you travel, 55 kilometers. So you see what I've done here is, even though I've shorthanded it, 55 kilometers per hour, I've just written out explicitly all over 1 hour. Now that I have that, it's not as hard to see my fractions, how they're going to cancel out. Well, my first fraction, I have kilometers. I don't want kilometers on top anymore. I want meters on top. So kilometers has to go on bottom to cancel out. That's just prefix to base unit, so I can do that in one conversion. Similarly here, hours currently is on the bottom. To cancel it out, I need another separate fraction. Again, it feels weird because I'm going through just putting the units. I'll worry about the numbers later on. But careful, because this hour here is on the bottom, I actually want to put the hour term on top to cancel it out. In that case there, you might actually know how many seconds in an hour, 3600. If you don't know that right away, you could even go, because I can tack on as many fractions as you want, I can first go hours to minutes. No, I don't want minutes anymore. Put minutes up here, seconds down here. So just introducing to you some of the variety, some of the advantages of setting up with this sort of conversion method. Let's go through and stick a 1 beside the thing that's bigger. So kilometers and meters, I know kilometers bigger. Hours and minutes, I know hours bigger. Minutes and seconds, minutes and seconds. So the units are already set to cancel out. I just went through, I compared each pair, and I decided which is bigger, sticking a 1 beside it. Sometimes it's on top, sometimes on bottom, just to make sure the units cancel out properly. This will make sure you end up multiplying and dividing where you're supposed to. We had said from previous here, 1 kilo is 1,000. If I ended up throwing in like a centi or a deca or some other prefix, you can look it up at the chart for the time being, although eventually you do want to memorize those prefixes. In this case here, 1 hour, sometimes I get 30 minutes as an hour, no, 60 minutes in an hour, and also 60 seconds in a minute. And be really careful as you're typing this in. Numbers on top you multiply, so I can go 55, press the multiply 1,000, no problem. Any numbers on the bottom you end up dividing, so I go divide 60. Sometimes when people think about this one here, oh, I'm dividing 60, I'm already down here, they accidentally end up putting times 60 here. Your calculator doesn't understand this part. If you put it times, it thinks your 60 is at the top, because times is supposed to be on the top. So it might feel a little bit weird here. What you can do is you can go divide 60, divide 60. Every time it's on the bottom, you just press divide. After you crunch that through there, we get 55 divided by all these fractions here. Calculator does it exactly. So I'm just going to round it here. It's roughly 15 meter per second. Right? So all the other units cancel it out except meters on top and seconds on bottom, exactly what you want. This is more so a shout out to physics. Because our odometers are always in kilometers per hour, because we always need to put in SI units, this conversion is going to be used very often. If I'm having to show 3 fractions every single time, it's super cumbersome. I'll show you a shortcut just for this exact conversion. Even if one of these are different, if one of these have been a centimeter or something like that, you can't use it. But for this exact conversion, kilometer per hour to meter per second, what I can think about here is 60 times 60 is actually 3,600. There is picking up a factor of 1,000 here. Let's divide the top by 1,000, divide this by 1,000. I get the magic number of 3.6. And now all I need to remember for myself here is kilometers per hour. The magic number for this conversion, all these 3 fractions boil down to 3.6. It's divide to get to meter per second, or it's multiply to get back up to kilometers per hour. So just for convenience for physics here, you can just use the 3.6 here. Just careful to watch when it's multiply, when it's divide. For me, I just think about the number that goes with meter per second is always tinier. So if they give me 55 kilometers per hour, I know to divide. If they give me 15 meters per second and they ask for, oh, what would this be on my car odometer, you would then multiply by 3.6 as well. And that saves you the hassle of having to write out all 3 of these steps here. All right. One last conversion, just to show you all the versatility of setting up this way. Let's say I want to convert here, how many centimeters squared in an area that's 3 meters squared. So let's start off with a picture first. Right away, these areas here are two-dimensional, so this is a little bit harder. What I want to know here is if I have a square that is 1 meter on every side, 1 meter, 1 meter, the area multiplied 1 times 1 would be the area of 1 meter squared. So I happen to have 3 of these meter squares. What I want you to convert to is I want you to convert it to, if you count just 1 centimeter and 1 centimeter, the area of a tiny square here, if I have 3 of these red tiles here, how many green tiles would I need to actually fill in this area here? If you plop this green tile here, this 1 centimeter on all sides, it's not going to cover a lot of the area. So what you can do here is you can say, well, I know I need 100 centimeters to make up a meter, which means what I would need to do is I need to multiply it by 100 to get you just that dimension there. I get a whole row. But that isn't the whole area. That's just one of the 2 dimensions. So what you need to do here is you need to say, well, for the other length as well, 1 centimeter, I also need to multiply it by 100 to get all the way along this way. I'm actually going to multiply the same conversion twice to actually get the entire area. Let's see how our unit conversion method shows it to you here. We want to know how many centimeters squared. How many green squares if I have 3 of these red squares here. What I want to start off with is the number and the unit, 3 meters squared. Don't write this down just yet. You want to convert here, oh, the unit I don't want is meter squared, the unit that I want is centimeter squared. It's just with that next step with unitary rates here, you may not know this conversion off the top of your head. You may not know how many green squares would fit automatically on the red square, especially if one of these units were a lot different. What I'm going to do instead is I'm actually going to use the one-dimensional conversion. I'm going to say I do know 100 centimeters is 1 meter when it's to the power 1. So instead of converting the square to the square, let's convert just meter to seconds. So one of the bigger unit is 100 centimeters, and let's actually do the same conversion twice. Because a meter squared is meter times meter, that meter squared will cancel out the meter times meter. I'm going to pick up a centimeter, I'm going to pick up a centimeter, and I'm going to end up with centimeter squared. If you want to be really elegant with this part here, you can actually say 100 centimeters, 1 meter, all squared. It's basically doing the same conversion twice. You multiply the 100 the first time just to get the horizontal. You multiply 100 the same number the second time just to get the area. And the same thing can be extended to cubes as well. So let you finish that off there. You should get 30,000 centimeters squared. All right. So practice some of these conversions here on your worksheet here. On your worksheet, you will have some imperial conversions as well. You don't need to memorize things like pounds and inches, things like that, but given those relationships, you should still be able to do this practice with unit conversions. If you have any questions, just let me know. Thanks, guys.